A Chinese cargo plane recently finished the very first flight in the world, powered by a megawatt-class liquid hydrogen turboprop engine. It spent 16 minutes in the sky, traveling 36 kilometers at a height of 300 meters above Jojo Airport. Allow me to translate what this actually means without all the technical jargon. For 3 decades, the aviation world has spent billions of dollars to reach one conclusion. Using hydrogen for propulsion is physically possible, but strictly impossible for business. It was considered too heavy, too freezing, too pricey, and completely reliant on facilities that simply did not exist. This recent flight didn't merely question that final ruling, it completely shattered every single assumption that ruling was based upon. If you want to figure out how a project that Western aerospace experts brushed off as being 10 years behind schedule managed to fly a functional plane, and what this implies for every single hydrogen aviation plan sitting on government desks right now, make sure to subscribe and hit the notification bell, because the airplane itself isn't the real story here. The system that made it fly is, for dozens of years, aerospace engineers worked under a shared belief, backed up by so much data, that arguing against it felt more like fantasy than actual science. The standard argument was that hydrogen was a brilliant fuel in theory, but a total disaster in practical flight. Nobody argued with the physics. Hydrogen holds about 2.5 times more energy per kilogram than normal jet fuel. We are talking about 120 megajoules per kilogram compared to roughly 43 for standard kerosene. If you only look at weight, hydrogen is the clear winner. However, airplanes don't fly based solely on weight. They also rely heavily on volume. And when you look at volume, the whole situation flips upside down. Liquid hydrogen packs about 8 megajoules per liter. Standard jet fuel holds roughly 34. To transport the exact same amount of energy as a full tank of kerosene, a hydrogen plane needs a fuel container, about 4 times bigger. Imagine taking the fuel tanks on a standard commercial passenger plane, ripping out everything else inside the main body, and packing that whole area with highly insulated, deep freeze storage tanks. Even then, you wouldn't match the original flight distance. That is not just a simple design hurdle. That is a complete rewrite of what an airplane structurally is. Then we have to talk about the freezing issue. You have to store liquid hydrogen at -253 degrees Celsius. That is barely 2 degrees above absolute zero, the absolute bottom limit of all heat energy. Reaching a freeze that deep requires active cooling machines, and those machines come with their own added weight, their own power needs, and their own ways to break down. The padding around the fuel tank has to be incredibly thick to stop heat from leaking in from the plane's outer shell, which could easily sit at +40 degrees Celsius or higher on a sunny runway. You are looking at a temperature gap of nearly 300 degrees across a barrier that is only centimeters thick. Material science simply does not have a ready-made solution for that kind of extreme temperature clash while staying lightweight enough to fly. Boeing took a hard look at hydrogen engines back in the early 2000s and decided that fitting them into a plane body was an impossible puzzle if they wanted to keep the weight commercially reasonable. Airbus ran its own inner checks on hydrogen over several different testing periods and kept pushing the target dates further back. In its 2019 environmental study, the International Civil Aviation Organization labeled hydrogen engines as a future tech that would need massive ground facilities and safety testing before any real-world use. They placed that target date safely past the year 2040. These were not overly careful groups, just playing it safe. These were the exact same organizations that built the safety standards for every single commercial flight taking off today. When they claimed hydrogen wasn't ready to go, they weren't just guessing. They were reading their very own test data. The financial side of things only made the physics problems look worse. Green hydrogen, which is made using renewable energy and water, is the only type that actually gives you zero emissions. Back in 2020, even in the best-case scenarios, it was selling for anywhere between $8 and $12 per kilogram. Standard jet fuel, even when prices are spiking, costs less than $1 per kilogram when you match up their energy output. You cannot close a price gap like that just by making engines a tiny bit more efficient. It demands a total rebuild of how we produce and ship hydrogen everywhere. Absolutely no single aircraft project could build that kind of economy by itself. But the biggest roadblock wasn't just physical reality. It was all the rules and red tape. There was literally no official way to get a hydrogen-powered commercial plane approved to fly. Aviation authorities in China, the United States, and Europe simply had no rulebook for deep-freeze fuel systems in planes that carry people. Creating that rulebook would take years of legal work happening right alongside the engineering tests, with absolutely no promise that both sides would finish at the same time. The general aerospace view wasn't just negative. It was being brutally honest about the massive size of the hurdle. And that exact honesty is what made the next event so incredibly hard for the industry veterans to wrap their heads around. The project behind this recent flight didn't just pop up out of nowhere. Back in 2021, the Aero Engine Corporation of China, or AECC, the massive state-backed group handling every big engine project in Chinese skies, officially announced they were working on a hydrogen-burning engine. Their target was a megawatt-class turboprop. They clearly stated they weren't building a small science fair model. They wanted a real, flight-ready engine that could hook straight into current cargo drone designs. Western aviation news caught the announcement, shrugged, and moved right along. The general mood, if anyone cared at all, was calm disbelief. Burning hydrogen inside a turboprop engine was a path engineers already understood. But the timeline AECC hinted at, going from the start of the project to a flying plane in under 5 years, was viewed as a joke by the big institutions that had spent decades looking at the exact same math and giving up. The doubts were very specific. Burning hydrogen inside a gas turbine creates nitrogen oxide pollution at high heats, which messes up the whole zero-emission selling point. Liquid hydrogen needs serious airport gear, like ultra-cold tanks, special hoses, and venting safety rules that almost zero commercial airports actually have. On top of that, getting a hydrogen engine legally cleared to fly under China's rules, much less global rules, was a completely blank page. These weren't just theoretical worries. These were the exact same walls that caused every single Western hydrogen project to stop dead in its tracks. They said the exact same things about China's bullet train plans back in 2003. We all know how that turned out. What the doubters failed to notice was how the actual project was put together behind the scenes. AECC didn't look at hydrogen flight as just a simple engine puzzle. From the very first blueprint, they treated it as a massive, connected system challenge. The engine that ended up flying in Jojo, called the AEP-100, was built right alongside a whole new way to pipe liquid hydrogen, a set of rules for handling the ultra-cold fuel on the ground, and a study on how to fit it all into a plane body made by Air White Whale, the cargo drone maker that provided the test plane. Top engineering schools like Northwestern Polytechnical University and Beihang University brought in their smartest researchers to figure out heat control and stable burning. This wasn't just a single project. It was 4 separate projects racing forward at the exact same time to make one flight happen. The critics were too busy looking at the fuel itself. They completely missed the giant machinery being built to handle it. The first hurdle AECC tackled sounds incredibly easy until you spend half a minute thinking about it. A normal engine-burning jet fuel pulls room-temperature liquid from the wings, sprays it into a fine mist, and lights it on fire in the chamber. Dealing with the heat of that delivery is pretty basic. Now, swap that normal fuel for liquid hydrogen sitting at -253 degrees Celsius and try sending it down those exact same pipes. When it hits the sprayer, it doesn't just burn. It changes form completely. The liquid hydrogen turns into a gas way faster than the system can handle, creating huge pressure spikes that no engine chamber is built to survive. Imagine dumping liquid nitrogen straight onto a red-hot iron pan. The liquid doesn't just bubble, it flashes into vapor violently, and that explosive force has to go somewhere. In a jet engine, that explosive force hits the fragile turbine blades. To fix this on the AEP-100, AECC created a step-by-step heating system right inside the fuel line before it even reaches the fire. The ultra-cold liquid leaves the tank and runs through a heat swapper. This device steals leftover heat from the engine's exhaust to warm up the fuel in a very careful way. It doesn't warm it to room temperature, but to a highly stable, pressurized state where the hydrogen acts like a thick gas instead of an unpredictable freezing liquid. By the time it hits the sprayer, it's no longer a cold liquid ready to explode. It is a steady, high-pressure gas that burns exactly how they want it to. Ground tests released right before the big flight proved that the pressure inside the firing chamber stayed steady within 2% across all power levels. That kind of steadiness matches the safety numbers of older kerosene engines that have been flying for decades. The temperature jump handled by this heating system was over 270 degrees Celsius in less than a meter of pipe. The materials doing the heavy lifting included super tough nickel alloys on the hot exhaust side and extreme cold stainless steel on the hydrogen side, separated by a special layer to control the heat flow perfectly. That 2% pressure swing isn't just a hopeful test score. That is a number ready for factory production. However, fixing the heat issue created a brand new headache that the engineers saw coming from day one. The heating system added bulk, and when it comes to flying on hydrogen, keeping things light is the only way the math works out. Every single ounce added to a hydrogen plane's fuel setup is a penalty you don't really face with regular jet fuel. Since hydrogen takes up 4 times as much space as kerosene for the same energy, the plane is already dragging around a much larger, heavier tank just to fly the same distance. Add in heat swappers, thick insulated pipes, and pressure valves, and that weight penalty starts stacking up fast. When the AECC team did the math on their finalized heating setup, they hit a total weight that practically wiped out all the benefits of using hydrogen in the first place. The clever system that stopped the fuel from exploding had caused a weight crisis that the plane couldn't handle. The normal way to fix a heavy tank is to swap out the materials, trade heavy steel for lighter aluminum, shave the walls down as thin as safely possible, take the minor weight savings, and call it a day. AECC ignored that rulebook. Instead, their team suggested a structural flip that sounds absolutely crazy at first glance and seems like it would create more trouble than it's worth. Normally, you drop a pressurized fuel tank inside the plane's body, which means both the tank and the outer plane shell have to be strong enough to handle their own separate stresses. The engineers proposed making the actual wall of the tank act as the main structural support of the airplane itself. The tank wouldn't just sit inside the frame. The tank would literally become the frame. The magic ingredient making this work is carbon fiber reinforced polymer, or CFRP. By weaving these fibers in a very specific pattern, they could adjust the strength to handle the intense pressure of the freezing fuel and the bending force of the wings at the exact same time. The very same shell that locks in liquid hydrogen at negative 253 degrees Celsius is also holding the wings steady while flying. There is no backup support layer. There is no separate fuel container inside. Both jobs are being done by the exact same material in the exact same space. Tests run by AECC before the Jojo takeoff proved that this combined carbon fiber body could handle 5 bars of pressure at ultra-low temperatures without bending out of shape. At the same time, it chopped about 23% of the weight compared to using a traditional separate tank of the same size. It honestly sounds like something that shouldn't be possible, and that is exactly why it works so well. So, both of these setups worked perfectly on their own. The clever heating rig tamed the freezing fuel, and the combined carbon shell fixed the massive weight problem. But testing individual parts in a lab and flying them bolted together in the sky are two completely different beasts. The massive headache of running an exhaust heat system and a structural fuel tank at the exact same time isn't obvious when you only look at the ground numbers. On their own, each piece acts normally. The heater pulls just enough waste heat to manage the fuel's temperature. The carbon tank holds the intense pressure safely. But up in the air, these systems aren't isolated at all. They are chained together. The amount of heat the warming system pulls depends on how hard the engine is working. How hard the engine works changes with every single stage of the flight, taking off, cruising, and dropping down. Every shift in engine throttle tweaks the heat available for the fuel, which changes the temperature of the hydrogen hitting the injector, which alters how the fuel burns, which feeds right back into the engine's power, which changes the physical stress on the plane's wing frame, which finally alters the cold barrier on the inside of the carbon fiber tank. These two systems don't just exist side by side. They are locked in a constant physical conversation. The old-school way to handle this kind of chaotic loop was to play it incredibly safe. You keep every system running well below its limits, so the wild swings never get out of hand. It works, sure, but it also guarantees your plane will never run at top efficiency, because all those safety buffers chew up the performance. AECC's engineering team knew early on that playing it safe would result in a plane that proved the physics worked, but totally failed as a practical commercial product. That wasn't acceptable. So, AECC built a real-time hydrogen energy brain. This onboard computer constantly tracks the temperature of the fuel lines, the physical stress on the tank wall, the pressure in the burn chamber, and the engine's demands all at the exact same time. It runs a predictive loop so incredibly fast that it stops problems before they even happen, rather than just reacting after the fact. Taking in data from over 40 different sensors, it tweaks the fuel pressure and the heat transfer in mere milliseconds, keeping both systems running smoothly at maximum efficiency instead of sacrificing one to save the other. The final flight numbers from the Jojo demonstration proved this setup delivered an 11% boost in fuel efficiency compared to the ground tests where the systems weren't synced up. That isn't a hopeful projection. That is hard data, pulled straight from AECC's official post-flight review. This combo, the heat manager, the structural tank, and the real-time brain, created a result so solid that AECC's own team demanded a second review of the numbers before showing the world. Now, let's look at the raw truth of the situation. The Jojo flight was only 16 minutes long. It flew 36 kilometers at an altitude of 300 meters. The aircraft was a pilotless cargo drone weighing 7.5 tons. This is not a passenger airliner, and you won't see it on a departure screen anytime soon. The AEP-100 engine does not have a timeline for commercial passenger flights. AECC has openly admitted their immediate focus is strictly on unmanned cargo drops to remote or island areas. The distance it flew is a tiny fraction of even the shortest regular flight in China, and the liquid hydrogen fueling station they use to fill it up only exists at one single facility. These are massive real-world roadblocks, and they are not small. But here is what the Jojo flight actually proved, as verified by AECC and reported on the news. It was the absolute first time a megawatt-class liquid hydrogen turboprop engine successfully worked in the sky. An engine pumping out over 1 megawatt of power from burning hydrogen, perfectly synced with an ultra-cold fuel delivery system, a load-bearing tank frame, and a lightning-fast computer brain, all functioning flawlessly together in midair. The Chinese aviation authorities haven't officially stamped it for full commercial use yet, but the flight logs from this test make up the very first complete, real-world data package of its kind anywhere on the planet. Put that into human perspective. A 36-kilometer jump right now is exactly how the very first turboprop engine tests started out, before evolving into regional planes, flying 800 kilometers just 2 design generations later. The routes this kind of plane would tackle first, like Chengdu to Chongqing, or island hopping in the South China Sea, are some of the absolute busiest short flights in China. 0 carbon emissions in the air, only water vapor coming out the back. On those routes, operating on a massive scale, you aren't just reducing pollution slightly, you are erasing it totally. A week before the flight, on the 29th of March 2026, their ground tests showed the engine running flawlessly from resting idle to absolute maximum power, without a single accidental shutdown across the entire test run. That isn't just proving the tech works. That proves it has endurance. The true ceiling was never the laws of physics. It was making all the pieces play nice together, and those pieces just flew. Breaking a flight record alters a single line on a spreadsheet. What happens next is the massive question every aviation department globally started asking the day after the flight. Air travel is responsible for roughly 5% of the world's carbon emissions. A statistic standard, environmental reports always quote, but that number actually hides the true damage. When you factor in the nitrogen oxides, the vapor trails, and the cloud formations high up in the atmosphere, the real climate impact is closer to 4% of all human-driven warming. For an industry promising to hit net zero by 2050, the massive void between those promises and the actual tech available has always been the main nightmare. Alternative aviation fuels cut down emissions over the fuel's lifespan, but they still burn dirty. Big batteries fix the pollution issue, but are far too heavy for anything longer than a quick, ultra-light jump. In the official rulebooks, burning hydrogen was always classified as a distant dream, something we'd absolutely need someday, but wouldn't be ready anytime soon. The places paying closest attention to the Jojo flight aren't the ones with the biggest aviation industries. They are the ones with the biggest short flight headaches. Southeast Asia, with its endless archipelagos relying on short flights that barely make financial sense on regular jet fuel, has the most urgent need for a cheap hydrogen plane. India, struggling to connect smaller regions because fuel costs chew up the profits, is right behind them. China's own layout of endless short trips under 500 kilometers makes it the perfect launchpad for real-world use. But truly rolling this out requires more than just a brilliant engine. It demands an entire, parallel hydrogen supply chain built from scratch. We need deep freeze storage tanks at local airports, hydrogen factories close enough to deliver the fuel affordably, and a unified set of safety rules across countries that currently have zero standards for this tech. Airbus has already started mapping out this exact massive gap by teaming up with hundreds of airports for their own 2035 zero-emission goal. But the gap Airbus is busy drawing on a map is the exact same one AECC just successfully flew straight through. Back in 2010, energy experts predicted solar power would match the price of standard electricity by 2050. They actually hit that target in 2015, a full 35 years early. Those old predictions claiming hydrogen flight would take until 2040 are now sitting right next to those completely wrong solar guesses. The massive edge China gained after Jojo isn't just a clever patent for a fuel sprayer. It is an entire, completed chain, making the fuel, storing it, pumping it, burning it, building the plane around it, and getting the official flight data, all constructed and proven at the exact same time. Duplicating that entire chain takes significantly longer than copying any single component within it. The conversation is no longer about whether hydrogen flight is possible. It is strictly about who is going to build the infrastructure that makes it an everyday reality. If you are still watching, you now know more about the reality of hydrogen flight than the majority of people who write about it for a living. You understand that this wasn't just a 16-minute joyride over a Chinese airport. You understand what this test actually proved. It proved that the three most brutal hurdles in hydrogen flight, delivering freezing fuel, handling the massive structural weight, and balancing the whole system in real time, can be solved all at once by a team that builds the solutions side by side instead of one after the other. That is not a tiny step forward. That is a total validation of a completely new way to tackle impossible engineering roadblocks. This flight doesn't mean you will be boarding a hydrogen passenger jet next year. The short range is a reality. The lack of ground gear is a reality. The mountains of red tape are a reality. What it does mean is that every single aerospace group on Earth that confidently pushed hydrogen flight past the year 2040 is now dealing with the fact that a 7.5-ton drone just proved their timeline completely wrong. If you come here for exactly this kind of breakdown, the real engineering hiding behind the headlines, the clever systems breaking the records, and the massive ripple effects the PR statements completely ignore, then make sure to subscribe and hit the notification bell. It truly is the best way to ensure you don't miss the next video. We will be tracking the AEP 100 program closely as AECC hands over their data for official certification. And when that major update drops, you will want to already be here. There is a massive debate brewing right at the core of this Jojo result, and I want to hear your take on it. One camp believes China's lead in hydrogen aviation is rock solid because it's a complete system advantage. They mastered the engine, the frame, the fuel, and the rules altogether, and catching up to a fully connected system takes a decade, even if you understand the individual parts. The other camp argues that the gap in real-world commercial use like flight distance, passenger space, airport gear, and global laws is still so massive that this flight is just a cool lab trick, not a market takeover. They think Airbus and the West have the massive funding and political weight to close that gap, long before these planes actually start selling. Both sides make a really solid argument. Let me know your answer in the comments below. I read every single one of them. Catch you in the next video.